So we're very happy to have Caucher Birkar from Cambridge University, who's going to tell us about singularities and Fano varieties in birational geometry.
Okay, thanks a lot. First of all, I would like to thank the organizers, Professor Yao and Professor Chow, for inviting me to this really nice conference. Most of the people here are differential geometers, so I will try to be very non-technical, to tell you essentially to report on recent progress in birational geometry. Let me start with the plan of my talk. First, I will try to give you an overview of birational geometry, discussing canonical divisors, special type of varieties, and then I tell you how the picture looks like in dimension 1, and then I'll tell you what we expect in higher dimensions. And then after that, I will describe the minimal model program, which is a sort of algorithm to tell you how to essentially classify varieties in higher dimension. And then I will talk about singularities of varieties, but also of pairs, varieties together with divisors. And then I will talk about Fano varieties and some of the main results. And then finally, if there is time, I will give you some ideas of the proofs involved. Okay, first of all, let's work only over the complex numbers. This is not really necessary. You can work over any algebraically closed field of characteristic 0 or conjecturally over any algebraically closed field. In fact, even over probably arbitrary fields or maybe over some more general schemes. But for simplicity, let's work over the complex numbers. Now, in this talk, by a variety, I mean a quasi-projective algebraic variety defined by polynomial equations in some projective space. And then two varieties are called birational if they have isomorphic open subsets. And so over the complex numbers, this just means these two varieties are meromorphic. So it's an essentially analytic notion. And then a birational geometry aims to classify algebraic varieties up to this birational transformation, birational isomorphism. So the aim of algebraic geometry is to classify algebraic varieties in general. However, it's understood even in dimension 1 that this is just impossible. You cannot classify all varieties up to isomorphism, so you will allow some flexibility, and this flexibility exactly means this birational isomorphism. So in practice, this means that in each birational class, you look to find some nice representative, some nice model, and then finally try to classify these nice models to get this birational classification of varieties. Okay. So one of the objects that plays a really central role in in birational geometry is the so-called canonical divisor. This is defined using differential forms, so it's very close to differential geometry. Now, every smooth or even normal variety X has a so-called canonical divisor. So this is defined as a divisor, as a class of divisors. You can take a top degree rational differential form and then move it around your variety. And then when you move from a coordinate chart to the next one, the changes in coordinates, the changes in the function that appear, give you a divisor. So you will get a divisor of zeros and poles, and you call that canonical divisor. To be more precise, the sheaf associated to this divisor is the so-called canonical sheaf, and at least in the case of smooth varieties, this is precisely just the determinant of the sheaf of differential forms. And if your variety has singularities, then you can define this on the smooth locus and essentially take its closure to the whole variety. Let me give you some very simple examples. If you take the projective space Pn, then its canonical divisor is just minus n minus 1 times a hyperplane. This H is a hypersurface of degree 1. So it's a very simple object in this case. And more generally, if you take any hypersurface of degree r in Pn, then its canonical divisor is just r minus n minus 1 times a hyperplane restricted to this variety x. So in the case of hypersurfaces, you can calculate this very easily. And more generally, if you look at complete intersections, you can again calculate the canonical divisor very easily. However, a random typical variety is very far from being a hypersurface or a complete intersection, so it's much harder to understand its canonical divisor. Now, also there is a more general example of toric varieties. For the case of toric varieties, the canonical divisor is just minus the sum of the torus invariant divisors. So again, in this case, the canonical divisor is simple, but this gives you a lot of examples of nice varieties and their canonical divisors. Now, next I define special varieties in terms of this canonical divisor. Suppose that X is a projective. Now I take things to be compact, a projective variety with good singularities. For the moment, I don't define what is a good singularity, so we can wait until later in the talk, but just assume that this is some kind of, there is a notion of good singularities. And then I say that X is a Fano variety if its canonical divisor is negative, or more precisely, anti-ample. And a prime example of such a variety is the projective space. And I say that X is a Calabi-Yau if Kx, the canonical divisor, is trivial. And these are all defined in a numerical sense. So this means numerically trivial. And again, a prime example of such varieties are abelian varieties. However, you should be careful that in some other parts of mathematics, abelian varieties are not called Calabi-Yaus because you put some more extra assumptions. But here, we are only interested in this numerical geometry, so canonical bundle being trivial means Calabi-Yau. For example, elliptic curves. And then finally, I said that X is canonically polarized if its canonical bundle is ample, or in other words, positive. And these are numerical definitions, therefore they just correspond to the fact that real numbers, there are only three types of real numbers: positive, zero, and negative numbers. And it's really amazing that this gives you three fundamentally different types of geometries. And in fact, one of the main aims of birational geometry is to show that every variety is somehow birationally, you can break it into pieces where all the pieces are in one of these forms. So there will be Fanos, Calabi-Yaus, or canonically polarized. And let's look at one simple example. If you take a hypersurface in Pn of degree r, then, oops, oh, what happened? You have seen already half of my talk. OK, so in this case, the picture is very simple because hypersurfaces are very simple. Then you just look at the degree of this hypersurface. If the degree is less than n plus 1, then X is a Fano. If the degree is exactly n plus 1, then X is a Calabi-Yau. And if the degree is more than n plus 1, then this X is canonically polarized. So in this case, every hypersurface is naturally one of these special type of varieties. And by the way, this terminology special is not commonly accepted, so it's only for the purpose of this talk. There was no other appropriate word. OK, now these kind of varieties are very interesting in birational geometry that we will see in a minute, but these are not really restricted to their interest to birational geometry. More generally, in algebraic geometry, they basically appear everywhere. For example, in derived categories, Professor Kawamata will talk about that soon in this conference. And they appear, oops, again. in moduli theory. So moduli, again, in a way you could consider that as a part of algebraic geometry. For example, moduli of curves or moduli of varieties of general type. And in fact, there is also a close relation with Hodge theory. For example, if you look at moduli of Cauchy-Birkar, how they vary in families, then you get this deep and natural connection with Hodge theory. For example, at some point in the talk, I will talk about the canonical bundle formula, and that's really just coming from Hodge theory. And then differential geometry. In differential geometry, these type of varieties are also very interesting. For example, existence of Keller-Einstein metrics, stability, for example, of Fano varieties that is a very popular subject. And then arithmetic geometry. So if you talk about existence or density of rational points, for example, on Fano varieties, is a really fascinating, still conjectural topic. So for example, you expect that on a Fano variety, you should have many rational points. On a Cauchy-Birkar, you expect again to have many rational points. But on canonically polarized varieties, you expect to have very few rational points. And the connection between geometry and these arithmetic properties are still largely conjectural. And then finally, we also have mathematical physics. In string theory and mirror symmetry, first Cauchy-Birkars play a fundamental role. But more recently, people also talk about mirror symmetry on Fanos and also on varieties of general type. So these special varieties appear basically almost everywhere in geometry. But in this talk, of course, I am going to focus on birational geometry. So let's see what happens in dimension 1. By dimension here, I mean the complex manifold, if the variety is smooth. Now, the good thing about dimension 1 is that if you pick any birational class, then there is a unique smooth projective curve representing that class. And that already kind of tells you that half of your job is already done, because you don't have to look for a nice representative. This one is the nicest possible representative. So you can just focus on smooth projective varieties, curves. So in other words, like compact Riemann surfaces. Now, the genus of a smooth projective curve can be defined in many different ways. You can define them as sections of the canonical divisor, or as the first cohomology of the structure sheaf, or you can define it more topologically as the number of holes if you consider X as a compact Riemann surface. And this number genus somehow reflect the geometry of varieties in dimension 1. In fact, if the genus is equal to 0, that exactly means that the degree of the canonical bundle is negative. And that precisely means that X is Fano, just by definition. And in fact, there is only one possible choice for such a curve, and that's just the projective line. If the genus is 1, that means the degree of the canonical bundle is 0. So in other words, the canonical divisor is trivial. That means that X is a Cauchy-Birkar by definition, and finally, X is an elliptic curve. And if the genus is more than or equal to 2, then the degree of the canonical divisor is positive, so X is canonically polarized, and maybe you can call such curves of general type, because there is a similar notion in higher dimension. So already in dimension 1, we can see that we have 3 very different types of geometries. And of course, you can also characterize these geometries using purely differential geometric notions like metrics and curvature and so on. Now, so we know that these varieties fall into these 3 classes, and then the next thing you want to do is to study such curves individually. So you can get as much information as you can. For example, you can investigate the linear system defined by the canonical divisor. For example, it's a classical thing that people try to see for what kind of curves this canonical system gives you an embedding of X into some projective space. And that's already the case for most curves, but not for all of them. And then after that you get information about such varieties, then you can study these varieties also collectively in families. And that leads you to the study of moduli spaces of curves of a fixed genus. So in the case of genus 0 and 1, you don't have so many choices. But when the genus is more than or equal to 2, there is a huge number of smooth projective curves with given genus. But if you fix the genus, then the number of such curves is not, again, huge. In other words, they can be parameterized by an algebraic object of finite type, and that's just a moduli space of curves. And then, of course, you want to compactify such moduli space and so on. So this topic, even in dimension 1, is still not a finished business. And what do we expect in higher dimension? Now, in higher dimension, if you pick a random variety, it's very far from being a special variety. It's not Fano, it's not Caucher, it's not canonically polarized. So what we expect is this conjecture. It's a combination of two conjectures. I put them both together, which say that if you pick any variety, let's say W, then this W is birationally isomorphic to a projective variety, let's call it Y, with good singularities. So singularities here are necessary, it's not just a lot for fun, such that one of the following things happen. Either this Y admits a Fano fibration. So you have a fibration where the general fibers are Fano. Maybe some special fibers will look ugly, but most of the fibers are just Fano varieties. Or Y admits a fibration by Caucher varieties. And if these two fail, then Y should be canonically polarized. This is really a very, very strong statement. It just tells you what I was trying to tell you before, that if you pick any variety, then birationally you can break it down into pieces where all the pieces are Fano, Caucher, or canonically polarized varieties. Let me just mention some of the known cases of this conjecture. The dimension 2 case is, of course, now a classical thing. It goes back to the early 20th century, mostly the work of Castelnuovo and Enrica, but also later on more developed by Zariski, Kodara, and many other people. And the three-dimensional case is much more recent, is mostly done in the 70s, 80s, and 90s through the work of Kawamata, Kolar, Miyaoka, Mori, Reed, Shakurov, and of course, with contribution of many, many more people. For example, Fano himself, Hironaka by providing resolution of singularities, Itaka, Iskovsky, Manin, and so many other people that I cannot list here. And in high dimension, the conjecture is still open, but we know many things. Especially, we know the conjecture is true for varieties of general type. Now, I did not define what that means. That, roughly speaking, means that the canonical divisor is large enough. It's large, so we call them varieties of general type. For example, for curves, for dimension 1, this just means genus more than or equal to 2. And in this case, for varieties of general type in any dimension, we know the conjecture is true by work of myself, Caccini, Heiken, and McKernan, after works of Shakurov, and this is much more recent, this in 2006. Okay. Now, when you are given a variety, how you obtain this variety Y having these nice properties? This is done through the minimal model program. This is a kind of algorithm which you input a variety and then it gives you something at the end. This is not a computer kind of algorithm, but in every step it actually tells you what to do. When you run the minimal model program on this variety W, then this gives you a sequence of birational transformations, let's say W1 to W2, W3, and then finally you hope to arrive at Y. Now, these transformations can be of several different types. One of the types, for example, is just contracting a divisor. For instance, you have, for example, you have a surface, and then you contract a curve. This is just the classical minimal model program for surfaces. But there is a much more complicated type of transformation. These are called flips, where you don't contract any divisor, but you are still contracting something. And their existence proved to be really extremely hard. It was proved in dimension 3 by Mori, who probably was awarded a Fields Medal maybe mainly for that. But his proof, unfortunately, did not work in higher dimension. We had to come up with completely different methods. And now, anyway, so the required contractions, we know they exist. It goes back to the work of Kawamata and Shokurov. In fact, that was already proved in the 80s. And the flips that I just mentioned, it comes from this work of myself, Kashini, Heiken, and McKenna. Now, one of the important ingredients in this whole program is the so-called finite generation. That says that the algebra, which is defined by the section of all the powers of the canonical bundle, you put this into a ring, it becomes an algebra over the complex numbers, and this algebra is finitely generated. So it's essentially, it was a classical conjecture, maybe goes back to, I don't know, early 20th or even 19th century. But that is established not only this global version, but in fact the local versions are even more important for this program. So this is the simplest case that I have stated. Now, the problem with this minimal model program is that there are two big issues. One of them is the so-called termination. And that says that this program, this algorithm, stops after finitely many steps. And there is absolutely no obvious reason why it should stop. And people have been trying to establish this termination for, I don't know, for 30, 40 years. And it's a really, really stubborn problem. And then we also have the abundance. The abundance problem in this context means that, assuming that you have already established termination, say that if the canonical divisor is not positive everywhere, then why this variety must be fibered by Fano or Colabi-Yau varieties. And this is also really very hard to prove. And unfortunately, we don't have so many ideas what to do for the second problem. But the first one is much more promising due to more recent work that I try to explain. Anyway, by now that I have tried to tell you what is birational geometry and minimal model program, it should be clear to you that both topics, singularities and Fano varieties, are, in fact, they are central topics in birational geometry because they just appear very natural. Singularities appear during this run in the minimal model program. So even if you start with a smooth projective variety, in most cases, just in the first step, you will get something which is singular. So typically, the wi's and the y that you get at the end are singular varieties. They are not smooth anymore. So you have to just live with the fact that you have to deal with singularities. And Fano varieties, of course, they are one of the outcomes, one of the building blocks of birational geometry. So obviously, both are very interesting. However, these are also interesting on their own, even if you don't care about birational geometry at all. Fano varieties appear everywhere, singularities appear everywhere. So now, there is more to this story. There are, in fact, deep connections between Fano varieties, singularities, and so on. In fact, singularities, in a way, can be considered as a local analog of Fano varieties. So Fano varieties are global objects, but singularities are local. And more recent work of myself that I will try to explain establishes connection between these two topics, which finally, through work of Shokurov and myself, we hope to prove the termination conjecture if we understand these singularities enough. So there are precise conjectural formulations of these connections. And in a way, this maybe is one of the main motivations for myself to look at singularities and Fano varieties to finally to be able to establish this termination conjecture. And I think you should not be surprised if it is proved in the next couple of years. 2 years ago, we had almost no hope, but now it's really hopeful to be proved. OK, now let me tell you what singularities are in birational geometry. A pair, we define singularities not only for varieties, but for pairs. And in fact, this is one of the key ideas, one of the key ingredients of the success of birational geometry in the last 30, 40 years, is that you consider not only a variety, but a pair, a variety together with a divisor. That allows you to do induction. If you don't consider the divisor, then the induction process can be very, very complicated. A pair here means a normal variety. Normal is a type of singularity. And together with a divisor where the coefficients of this divisor are between 0 and 1. We don't allow more than 1 for reasons that may not be clear here. And then we can define singularities of such a pair by comparing it with a resolution. So that means that you take a resolution. You resolve your varieties through this work of Hironaka, and also you resolve the divisor. So you will get the nicest possible thing, and let's call that, let's say, phi from W to X. And then if you pull back Kx plus B, you can write it down in a just elementary natural way as the canonical divisor of W plus some correction term, which let's call it BW. And then the coefficients of this BW tell you how singular your pair is. In fact, the larger the coefficients of BW, the deeper the singularities are. And singularities, I mentioned a couple of times that singularities are good. In practice, that means that the coefficients of this BW should not exceed 1. And in fact, in many cases, we don't want it to be equal to 1, but rather less than 1. And that's where the connection with Fano varieties appear. We can define a more general notion of singularities. We say xb is epsilon log canonical. This epsilon is a non-negative number here. If every coefficient of BW is at most 1 minus epsilon. So here you want to create a gap between 1 and the coefficients of BW. So it's a very elementary definition, but of course, studying singularities here can be extremely complicated. Let me give you some very simple examples. If you take X to be a smooth variety and B a variety, a divisor with simple normal crossing support, then this is a good kind of pair. So its singularity will be, the coefficient here will be less than or equal to 1, naturally. Another good example is if you take a smooth surface and you take B to be a nodal curve. Again, this is an acceptable, a good kind of singularity. However, a bad type of singularity is if you take a smooth surface and a cuspidal singularity, a cuspidal curve. This is not good, because if you do these resolutions and so on, you see that one of the coefficients in this BW jumps over 1, so things become complicated. You don't want to allow this type of example. OK, now I will give you an example, in fact, a series of examples, and I really like this example because you can both see singularities and also Fanos at the same time. And the example itself is not that complicated. For every natural number n more than or equal to 2, let's consider this diagram where xn is just the cone over a rational curve of degree n. So a rational curve here just means P1, the projective line, but it can have different degrees depending on how it sits in some projective space. So it can, for example, P1 can sit inside P2 as a line, but it can also sit inside P2 as a conic. So you can have different degrees depending on where it actually sits. And then the cone here just really means cone in a very elementary sense. So this is your rational curve. And then you have your vertex somewhere, and cone just means connecting every point here to the vertex. That's a cone. It's a very simple object. And then if you blow up this vertex, you get one curve. And that curve is this E in this diagram. And you get a surface which is smooth. So Wn is smooth, but Xn is not. And from Wn to P1, you have a P1 bundle structure. So I can define these things in a more precise form. Wn, you can also define it as the projective bundle of O plus O minus n on the projective line. And then the E is the section given by this component O minus 1. And then Xn is, you can obtain it by contracting this curve E on Wn. So in other words, this is a reverse kind of process. Now, you can calculate, you can relate the canonical divisors of Wn and Xn by this formula. This is just a simple numerical calculation. The canonical divisor of Wn plus n minus 2 over n times E is the pullback of the canonical divisor of Xn. So here you can measure how singular Xn is. We don't have a boundary divisor here. So just you are measuring the singularities of the variety itself. And the larger n is, the deeper the singularity is, because n minus 2 over n, its limit will go to 1 if you take n to be very large. Yeah, but still they are good singularities. They are acceptable singularities. And now the thing is that if you take the set of all such Xn, this stopped working. Yeah, if you take the set of all such Xn, so we have here infinitely many of them, this is not a bounded family in terms of algebraic geometry. There is no scheme of finite type. There is no algebraic object of finite type parameterizing all these Fano varieties. The reason are simple, because if they form a bounded family, then this number n minus 2 over n must be in a finite set, but it is not. And therefore, this is not a bounded family of Fano varieties. Okay, so let me discuss Fano varieties in high dimension in a more general context. Now, one of the first main result is that this is due to myself and not so long ago, just last year, we say that for every natural number d, there is a natural number m, such that if you take x to be any Fano variety with these good singularities of dimension d, then minus mk has a section. So this is an effective non-vanishing kind of statement. And it's really nice, because this m depends only on the dimension. It does not depend on the type of the singularities. You just take one m for every dimension. Moreover, this is, in fact, you have a stronger statement. The linear system given by this minus mk contains some element with really nice singularities. More precisely, contains an element with log canonical singularities. So in other words, not only this minus mk has a non-empty linear system, but it also contains a nice element. And this, in fact, this was conjectured by Shakurov very long time ago, in the mid-90s. But in fact, this whole problem originates much earlier. At least it goes back to the maybe mid-70s, where Shakurov himself proved that if you have any smooth Fano threefold, then minus k already contains a smooth K3 surface. So this is a more general form of that in higher dimension. But he himself, Shakurov, proved the theorem in dimension 2. And together with Prohorov, they also partially proved it in dimension 3. Now let's look at the simple example of toric Fano varieties. In this case, you can in fact take M to be 1 for every toric Fano variety. And the reason is that because in one example, I told you that the canonical divisor of a toric variety is just minus the sum of all the torus invariant divisors. And the thing is that the sum of those torus invariant divisors is already actually a nice divisor. So M equal to 1 works here. However, for more general Fanos, you have to take a larger M. Even in dimension 2, M equal to 1 does not work for every Fano. Now, if you put a bound on the singularity in that theorem, then you can have a much stronger statement. In fact, for every natural number d and positive real number epsilon, there is M, depending on these two numbers, such that if X is any epsilon low canonical Fano of dimension d, then its linear system given by minus mk defines a birational map. Here, roughly speaking, this means that minus mk has a lot of sections. And this epsilon low canonical condition just means that I already defined it precisely, but that essentially means you bound the singularities. Yeah? Yeah, it's a good question. In fact, what I prove is a much stronger, much more general statement, which is not only in this global setting, but also in local relative setting and so on. And so there are objects which, in fact, I will define in a few minutes. They are called complements, and they make sense even in purely local situation. And then the theorem can be reformulated as boundedness of complement. So hopefully I will get to that point in a bit. Okay, and now we have this effective birationality statement here. Wow, this is crazy. Yeah, this effective birationality for any given natural number d and positive number epsilon. But we have the next theorem is even a much stronger. It says that for every given d and epsilon, if you look at the set of all the Fanos with epsilon low canonical singularities and of given dimension, then they in fact form a bounded family. They can be parameterized by an algebraic object of finite type. Of course, this implies the effective birationality theorem. However, the proof of this somehow relies on proving this effective birationality first and then proving this theorem. So that's why I state them separately. This theorem was known as the Borisov-Alexeyev or just BAB conjecture, which goes back to early 90s. And so the theorem itself implies immediately through work of Prohorov and Shramov a question of Serre on Cremona groups. So the question was that whether the Cremona groups in any dimension satisfy Jordan property, and the answer is yes if you have this theorem. Now, let me also mention some of the partial cases that was known. The dimension 2 case was proved by Alexeyev, and another proof was given by Alexeyev and Mori. The toric case was proved by the Borisov brothers, and that's where the name Borisov, Alexeyev, Borisov comes from, because I think both people claim they conjectured this first, and then as a compromise, they say, okay, let's put it as Borisov, Alexeyev, Borisov, so then they don't have to fight. So the toric case is just about combinatorics. And then the smooth case was proved by Kolar, Miyawaka, Mori, and in some cases Nadel, and in fact in dimension 3 by Fano himself. So the proof goes back to the 90s and earlier. And here, to prove the theorem, you apply Mori's techniques, bend and break techniques of producing rational curves on Fano varieties, and then you compare. You essentially say that through every point passes certain rational points with bounded degree, and therefore you bound the multiplicity of the divisors in, for example, minus k. However, this miserably fails for singular varieties, so it just doesn't work for the proof of the theorem. Anyway, for dimension 3 and epsilon more than or equal to 1, the theorem was proved by Kawamata, and a more general form of it by Kolar, Miyawaka, Mori, and Takagi. But also a very special case, which is not easy to state here, so I just don't state it, was proved by Haken, McKernan, and Xu. OK, now I come to the answer of the question, what are complements on Fano varieties? Suppose that X is a Fano variety, and then an M complement is of the form the canonical divisor plus some delta. Delta is some boundary divisor, where we assume these conditions, that X delta has good, in other words, low canonical singularities, and then this crucial assumption here that M times K plus delta is linearly trivial. So it's a torsion, K plus delta is a torsion divisor with torsion index divisible by M. So M, it should divide M. So this tells you that M times delta is a divisor in this linear system given by minus MK. So if you have an M complement, it tells you something about this linear system. So how much time do I have? Like 5 minutes? Or? I can go until 12? OK. OK, so let me skip this. There are some trivial examples. Let me just skip those examples. And then you can reformulate one of the theorems earlier I stated, saying that for every natural number d, there is M such that every Fano variety with good singularity of given dimension has an M complement. But as I was trying to say, that this is just an oversimplification of what we prove. The actual theorem is a much, much more general statement. And let me just try to give you some ideas of the proof, going maybe quickly. Suppose that we are given X and we want to find a complement for X. We can perform some birational transformations and then find some boundary divisor B such that XB as a pair has good singularities, and such that we have one of the following cases. We have 3 fundamentally different type of situations here. One case is when B has a component with coefficient 1 and minus K plus B is ample. Another case is when K plus B is trivial along some Fano fibration. And finally, another case is when X has bounded singularities for some epsilon independent of X. And each case requires a very different type of argument. Okay. For case 1, we apply the so-called divisorial adjunction, and the idea is to go on S and to try to lift everything back to X. Now, S itself is not necessarily a Fano variety, but it's close enough, not very far from being Fano. And sorry, this is really getting crazy. OK, let's go back to case 1. And the key point is that, so when you apply this adjunction, you get not only k as the canonical divisor of S, but plus some correction term. And that's one of the reasons we like pairs, not just one variety. And then the key point is to find complements not just for k, but k plus something. That means you actually have to prove a more general statement. But this anyway works if you use cohomology, vanishing theorem, and so on. You can lift your data to the ambient space. And then case 2 requires something very different. We have a Fano, we have X, and then together with a fibration. And the fibration, k plus b is trivial along the fibration. So we can define something, I call it Kawamata's canonical bundle formula. This is just a more general form of Kodara's classical canonical bundle formula. And what you get here is a discriminant divisor plus mz, which is a moduli divisor. And the name moduli divisor is for a good reason. This is really related to the moduli theory. And mz itself is given by Hodge theory. Now, the key point here is to find a complement not just for k or k plus b, but for k plus b plus m. Now, the problem is that this m is not an effective divisor. Its coefficients cannot be really controlled. So what you have here is not a pair in the sense that I defined. This is just a new structure. So you have to find complements. You have to deal with this type of more general structures. And I was maybe here extremely lucky here because I studied together with a collaborator exactly this type of structures just a few years ago. So I knew what to do at this point. And essentially what you have to do here, you have to basically develop birational geometry for this more new, more general structure. And then finally, for the case 3, where you have bounded singularities, then here you go through effective birationality statement that I discussed. Here the idea is that you take m to be the smallest number so that a minus mk gives you divisors with deep singularity, so that you can have a family of divisors sweeping through X and giving you the singularities of the L will give you a so-called low canonical centers, which will cover your variety. And if the dimension of these centers are equal to 0, then you can use multiplier ideal sheaves and vanishing theorems to make minus mk birational. And then finally, of course, you have to bound the number m. Now, the really difficult case is when the dimension of G is positive. And here you have to show that the volume of minus mk restricted to G is bounded from below. And the difficulty here is that G may not be Fano. It can be pretty much anything. It can be, you start with a Fano, but when you go to lower dimension, you get something which may not be Fano. And then you have to also control the singularities of this G. Now, the key point is that the G itself is birationally bounded. You show that it is up to birational isomorphism bounded, and then you should work on this birational bounded model, not G itself. So here we need to bound singularities on a bounded family. And for that, we need this result, which says that for every natural number d, r, and positive real number epsilon, there is t, so that if you pick any xb projective epsilon low canonical of dimension d, if you have any very ample divisor with bounded degree, and a minus b being ample, then the singularities of every element given by a. Now, the key thing is here, I don't have linear, but are linear. So this is an asymptotic statement. This is a statement not only about a, but all the possible multiples of a. And that's where the difficulty comes from. So it says that the singularities of all these divisors are somehow bounded. Now, the statement itself may look kind of simple, but in fact, it's a really very strong statement because first of all, it gives what we wanted to treat the case of the final case of the boundedness of complement, But also, the proof of this Borisov conjecture goes through this theorem. Moreover, it almost immediately implies a conjecture of Ambro about singularities on Fano varieties. And however, the proof of the theorem relies on very different type of techniques. So I don't have time here. I will just stop.